In this video, we will be looking at the distance between a point and a line. Now, before we get into that, we're going to refresh on a grade 10 concept, which is finding the distance between 2 points. Now, if we have 2 points in two-dimensional space, so we have point P with x1, y1, and point Q with x2, y2, the distance is just going to be the magnitude between those 2 points, or the vector created that connects those 2 points. So it will look like the distance formula from grade 10. So the square root of x2 minus x1 squared plus y2 minus y1 squared. There we are. And it's going to be the exact same thing if it were in 3D, except now we have that extra z component. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So that's really just your magnitude formula. So what is the distance between the points P and Q? Well, the distance will be the square root of, and I'm going to start with Q minus P for the x's, negative 2 minus 1 squared plus, now the y's, 4 minus 2 squared, and now the z's, 1 minus 3 squared. And then we'll just clean that up. So negative 2 minus 1 is negative 3, squared is 9, 4 minus 2 is 2, 2 squared is 4, 1 minus 3 is negative 2, squared is also 4. And then we get the square root of 17 units. And that's the exact distance. Now let's move on to finding the distance from a point to a line in two-dimensional space. So the point that we're going to be using is going to be P naught, and the coordinates are x naught, y naught. And our line is given in the Cartesian equation form. Now, in order for us to develop this formula, we're going to use our knowledge of the dot product and just SOHCAHTOA. So, first of all, we have our line here in blue. We have the Cartesian equation, and we're just going to say P1 represents a random coordinate on that line. And the reason I want this random coordinate is so that I can create this vector here, starting from the point we want to P1. Okay, so we have vector P naught, P1. Then we have this vector here, that is our normal vector, the one that is perpendicular to our line. So to derive this formula, we're going to start with the dot product between P naught, P1 and the normal. And the dot product between these two vectors is equal to the magnitude of the vectors times cos of the angle between them. Now, the distance we want is this distance here. I'll label it D. And on the side, just thinking of SOHCAHTOA because we have a right triangle right here. That distance is adjacent to theta, and that vector P naught, P1 is the hypotenuse of the triangle. So this is going to require the cos ratio. Cos theta in that triangle is equal to the distance I want divided by the magnitude of vector P naught, P1. And if I just cross multiply here, here is what we get. And actually, if you look at your dot product, we have those elements on that right side. So this here represents the distance. So I can rewrite this dot product as the distance times the magnitude of the normal. Well, now I can divide both sides by that magnitude. And here is what I have for my distance. The dot product between P naught, P1 vector and the normal divided by the magnitude of the normal. Now let me start cleaning this up and actually bringing some exact coordinates. Now, this vector p naught p1, I can write it as x1 minus x naught, comma, y1 minus y naught, dot, the normal is vector AB. And that's all going to be over the magnitude of the normal, which is the square root of a squared plus b squared. And now I'm going to do that dot product. So we'll have a that is multiplied with both x1 and x naught, and b with both of the y's. Now, just on the side here, first of all, I need to keep anything about x naught, y naught, because those represent the point that I'm trying to find the distance of from that point to the line. So I'm going to write the Cartesian equation with x1 and y1 in it on the side here. Here's your Cartesian equation. If I bring c over, then I know ax1 plus by1 equals negative c. So I'm going to replace these with negative c because I know that is true. So now I'm left with negative ax naught minus by naught minus c all over that magnitude equals the distance. Now you'll notice all three of the terms in the numerator have a negative there. Well, I can factor out that negative. And that will turn all the coefficients positive. And of course, this is a distance. You need a positive number. So I don't even care about the negative being there. It's kind of useless. And then to make sure that it's going to be a positive number, I'm going to take the absolute value of that entire numerator. And that's how we get this distance formula. The absolute value of you plugging in your point into the Cartesian equation divided by the magnitude of the normal. So let's give that a try. Determine the distance between point P and the line 2x minus 5y plus 2. So we need the absolute value. I'm going to take my Cartesian equation and I'm going to plug in 2 for x, 3 for y, and then the normal is 2, negative 5. So I need the magnitude of that. And now it's just a cleanup game. So we have 4 minus 15 plus 2, that's negative 9, and we're going to take the absolute value of that. In our denominator, we'll have the square root of 4 plus 25, so the square root of 29. And to clean that up, I know the absolute value of negative 9 is 9, and I'm going to rationalize the denominator while I'm here. And there's my exact distance. What about finding the distance between a point and you're given the line as a vector equation? Well, if that happens, I need that Cartesian equation first. So we're given the direction vector. Our normal vector, we need to flip 5 and 3, so 3 and 5, and change one of the signs. There we go. It's like taking an opposite reciprocal of a slope. So we know our Cartesian equation will be 3x minus 5y plus some c value. And now the only point I know on this line is 0, 2. Plug that in. And that's negative 10 plus c equals 0, c equals 10. And here is our Cartesian equation of the line, and our point is negative 1, 5. So we're finding the distance from that point to that Cartesian equation. So our distance will be the absolute value of 3 times negative 1 minus 5 times 5 plus 10 over the magnitude of the normal. So that's going to be 3 minus 25 plus 10, which is negative 18. And then we have 9 plus 25, so the square root of 34. So the absolute value is 18, and I'm going to rationalize at the same time. And in this case, I can go further because 18 over 34 can be reduced to 9 over 17. And there we are. There's our exact distance. So for this question, we had to work for that Cartesian equation first. And finally, before we go to 3D, determine the distance between the parallel lines 2x minus 3y plus 10 equals 0 and 4x minus 6y minus 12 equals 0. And I didn't have to tell you that the lines are parallel because we can just look at the coefficients of x and y. So looking at the normals, and you can see that you can just double the line 1 normal to get the line 2 normal. But that doesn't apply to the constants. That's how you know that they're not coincident and they're just parallel and distinct. Well, how am I going to do this? Because I'm not given a point. But you can always find a point on one of the lines, and then you're finding the distance from that point to the other line. And it doesn't matter what point you find because these lines are parallel. The distance will be the same regardless of the point. So I'm going to use line 1, and I'm going to let y equal 0, and I'm going to solve for x. So I'll have 2x equals negative 10, x equals negative 5. So I just found the coordinate negative 5, 0. Now I'm rewording the question, find the distance from negative 5, 0 to line 2. And now we can repeat the process. Absolute value divided by the normal, or the magnitude of the normal. So we're going to have negative 20 plus 0 minus 12, so the absolute value of negative 32 over 16 plus 36 is 52. Well, here we can actually reduce our radical. So 52 can be written as 4 times 13. So that would be 2 root 13. Now I can rationalize. And the 32 over 26 can reduce to 16 root 3 over 13. And there's our exact distance for this point to that line in 2D. And that's going to be the distance between these two parallel lines, regardless of the point. All right, let's move on to the three-dimensional space. So we don't have a Cartesian equation of a line in 3D, so we have to use the vector equation. And to develop this formula, we're going to use our knowledge of SOHCAHTOA and the cross product. So looking at my diagram here, here's the line. We know vector M is the direction vector. And then the point that I'm using is point P. And point Q is going to represent a random point on the line. So that way we can create this vector QP. We have our direction vector, and this is the distance we want. So thinking of SOHCAHTOA, my distance is the opposite. Vector QP, or the magnitude of QP, is the hypotenuse. So that would be sine theta equals my distance over my magnitude. And if I just clean that up, I would get distance equals the magnitude times sine theta. Now, I would like to bring that direction vector in here somehow because I might not know sine theta. So I kind of want to get rid of that so that I don't have to solve for an angle before I can find my distance. So that's where the cross product is going to come in. As a reminder, if I wanted to find the magnitude of the cross product between QP and the magnitude, it would be the two individual magnitudes multiplied times sine theta. And the reason I'm using cross product is because cross product is about sine, and we have sine in our equation right now. And I'm using the magnitude because the magnitude of the cross product will use sine. All right, and now I can see here's QP, here's sine theta. These represent the distance, so then I can just divide both sides by the magnitude of m. And there's your formula. The distance is equal to the magnitude of the cross product between the direction vector and this vector QP that is formed between a point on the line and the point we're actually given to find the distance from, divided by the magnitude of the direction vector. So let's give that a try. Here's point P, and here's our line. This vector here, I'm going to use it to get that point Q, and here's my direction vector. So I'm going to start off by writing out my vector QP. So I'm going to do the P coordinates minus the Q. So -1 minus 2, 1 minus -2, and 2 minus 3. And then vector M is 0, 1, 2. And now I'm going to find the cross product between them. So we want the cross product between M and QP. So 1, 2, 0, 1, 3, -1, -3, 3. That's going to be -1 minus 6, -3 minus 0, or sorry, -6 minus 0, 0 minus -3. Okay, so I have my cross product. Now I can start on my distance. My distance is going to be the magnitude of that cross product divided by the magnitude of the direction vector. And now it's just cleanup time. So we have 49 plus 36 plus 9, square rooted, 0 plus 1 plus 4. There we are. And I'll multiply top and bottom by the square root of 5, which is the square root of 470 divided by 5 units. All right, let's try another one. Determine the distance between the point 0, 1, 5, so I'll use that as P, and the line vector R equals 0, 6, 0, there's Q, plus S times that direction vector. All right, vector QP. So QP is going to be 0 minus 0, 1 minus 6, 5 minus 0. Our direction vector is 2, -1, and 3. So let's do our cross product. So we have -5 minus -15, so that's 10. 0 minus 10, -10 minus 0. There we are. And now magnitude. 10 squared plus -10 squared plus -10 squared, so that's the square root of 300, divided by the magnitude of our direction vector. So square root of 300 over 4 plus 1 plus 9, square root of 14. And the square root of 300 can be reduced because that's 300 is 100 times 3. The square root of 100 is 10. So there we are. And now I will rationalize. So 3 times 14 will give us the square root of 42. Now we can finish reducing that 10 over 14 to 5 over 7. So 5 root 42 over 7 units is the exact distance from that given point to that line in 3D. Now, the final little setup or scenario is finding the distance if you're given two lines in 3D that do not intersect. So you're not given the distance from a point to a specific line between two lines. If the lines were to intersect, well, in that case, their shortest distance is 0. If they were parallel and distinct, you can just figure out a point on that line and repeat the process that we just did. If they are coincident lines, well, the shortest distance is 0 because they're right on top of each other. But if they're not parallel, but they don't intersect either, we have skewed lines. So how do we find the distance between them? Now, before we talk about the formula, there are a few things that we need for notation. So when you're given your two lines, you'll be given them in vector equation format. And when you're given those vector equations, you'll know a point on the line and you'll know the direction vector. So your first line will have P1 as the point you know and M1 as that direction vector. Your second line will have P2 for the point and M2 for the direction vector. So here's our distance formula. You're going to be taking the dot product between the vector formed by the 2 points that you know on the skewed lines and the cross product of those two direction vectors. And you're going to take the absolute value of that dot product and divide it by the magnitude of the cross product between the two directions. So let's give that a try. So here's P1, here's P2, there's M1, there's M2. So I'm going to start by finding vector P1, P2. So 2 minus -1, 5 minus 2, 11 minus -8. There we are. I also need the cross product between M1 and M2. So I will do that on the side and set it up nicely and carefully. So that's going to be 3 minus 4, 2 minus -3, -6 minus 1. All right, now that we have our cross product and we have our P1, P2 vector, we can start with that distance formula. So we're going to do the dot product between the vectors we just found and the absolute value of them and divide it by the magnitude of the cross product we just found. Okay, so we'll have -3 plus 33 minus 133 all over 1 plus 121 plus 49, so the square root of 171. And now just time to clean it up. So in the numerator, we'll have the absolute value of -103, and that's 103. And then as I rationalize the denominator, I'll multiply top and bottom by 171, or the square root of 171. And there we are. There's our exact distance between these skewed lines that never actually intersect. So we saw quite a few different formulas in this video. So finding the distance between just 2 points in 2D or 3D, the distance from a point to a line in 2D using your knowledge of dot product and SOHCAHTOA. Then we saw from a point to a line in 3D using our cross product knowledge. And then finally, skewed lines distance in, of course, 3D.